Now for dealing with more than two treatment means, we're trying to determine if they're all the same versus at least one of them is different, or not all the same, however you wish to refer to it. We're going to deal with ANOVA, and that stands for Analysis of Variance, or One-Way Analysis of Variance. We're going to do this when we're dealing with just a single factor. So I'm going to have some requirements for that ANOVA. First and foremost, populations have to be approximately normal distributions. If you run into distributions which are significantly non-normal, this is going to run into problems. The population variances are the same, or standard deviations are the same, and again, that doesn't have to be the exact same number, just within testing wise they have to be close enough to not have a significant difference between the two. You have to take these samples as simple random samples, of course. The samples should be independent of each other, and you have to categorize these things in only one way. Now this is what we're testing. So before we were either testing a mu equal to value or mu1 equal to mu2. Now we have at least 3, possibly more, equaling each other. This could be 10, 20, however many you want. You're going to enter data into your lists and then run the ANOVA test, and I'll show you how to do that. Or you can just, in many cases, you'll just have ANOVA output. You'll have a table, and you'll have to look at the table and determine whether or not to reject the null hypothesis. Now, as always, if our p-value is less than or equal to alpha, we are going to reject the null. So that means at least one of the population means is different from the others, or you don't have all of them being the same. And as it was before, if the p-value is greater than alpha, we'll fail to reject, so we're stuck with believing that the means are equal. Alright, here's an example. So I've got a little chart down below. It's chest deceleration measurements from 3 different types of vehicles. Those classified as small cars, those are medium, and those are large. So we've got 3 different treatment means. So here's all the data, and here's the X-bar from each given list. The small cars, medium cars, and large cars. So our null hypothesis is that all 3 treatment means are the same. Our alternative hypothesis is at least one is different. I've got H1 instead of HA, but that's certainly fine. Our significance level is alpha, and that is going to be 0.05. Now this is kind of what the ANOVA table is going to look like, or some reasonable facsimile thereof. So this is for a single factor. We're going to have one line for treatment. That's typically your first line, so, or row for that matter. These are different things, and I'll talk about those in a minute. And then we have the error, and then we have the total of the degrees of freedom and sum of squares. So DF stands for degrees of freedom. SS stands for the sum of the squares, similar to how we would calculate, say, standard deviation or variance earlier on. MS stands for mean square, and MS in the treatment row is called mean square for total. It is calculated by taking the sum of squares in that row and dividing by the degrees of freedom in that row. So you see SST divided by K minus 1. Similarly with the error, we take the sum of squared for error and divide it by its degrees of freedom to come up with the mean square error. And the mean square error is essentially going to be our variance function, so that's what we're going to be dealing with. And this value F is the test statistic. Now I'm showing you how to use the p-value. Later on I'll show you how to use the F statistic to do the exact same thing. But that is always taken by the mean square of the row that you're in, and again there's only one factor here, so there's only going to be treatments, divided by mean square error. So the mean square error is always going to be in your denominator if you have multiple factors or whatever. So K is the number of treatments, and in this example we have 3 treatments, so our degrees of freedom will be K minus 1 or 2. And N is the total observations. So how many do we have? 1, 2, 3, 4, 5, 6. So we've got 30. N will be 30 here, so total degrees of freedom will be 29, and so forth. So this is kind of what the ANOVA table will look like. Now, here is an output value if the data is entered in Excel. The sum of squares and degrees of freedom are flipped. It also has a p-value in a chart. All right, so after the f value, we've got a p-value. That's what we're going to look at to determine whether or not we reject. And again, this is less than our 0.05 level of alpha, so we are going to reject. Another thing it's displaying is the f critical value. I'll show you later on how to find that on a chart. But your test statistic f here is greater than this f critical value, and we're always looking for a right-tailed test, so always a greater than. So we're going to reject based upon our traditional method as well. This is what it looks like if you use the TI 83 or 84 to output it. So we've got for factor, degrees of freedom, sum of square, mean square, and there's your f. And then if you page down for error, this would be our error row 27. You see there, the sum of squares 537, and then the mean square 19.88, and so forth. So this is kind of what it looks like, but the important value is, of course, the p-value, the 0.027986. That is going to cause us to reject the null hypothesis. And our p-value is less than alpha, so we have sufficient evidence to indicate a rejection from the null hypothesis. Now, let me move this over here. All right, so these are our data points, and I'm going to show you how to run the ANOVA on here as well. Now, I've already got the data entered, stat enter. I've got the data entered in list 1, 2, and 3, and the order of these doesn't matter, but again, I would always suggest doing them in the order that you see them. That way, if you've made a mistake and say your output, your display doesn't look like my display, you can find your error in the data entry easily. Medium and large cars are also in there. So to run the test, we hit the stat key, arrow over to test. I'm going to go up because it's the very bottom one on mine. H ANOVA. The H is the test, the letter, and ANOVA is what we have. So we're going to hit enter, and I need to give it all three lists. I have it in list 1, 2, and 3, so second 1 for list 1, comma, second 2 for list 2, comma, and second 3 for list 3. That's what you should have, and you're going to hit enter. And I'm going to go back to my PowerPoint here and show you that I have the same values here. So here my initial 2, 162.86, 2, 162.866, and so forth. Same p-value, same p-value. All right. So this is what we have here, and we can scroll down to see the rest of it and so forth. But again, we've got a p-value that's less than 0.05, so we're going to reject. So they're not all the same. Now, in order to determine which ones are different from each other, or which one may be uniformly better than the rest, we're going to take the actual values, the actual means of each of these, and figure out the largest one. In this case, they're in order. Small had the largest one, then medium, then large. Okay? So, for this, I'm going to put S, then M, then L, or if you want, you can have mu1, mu2, mu3, whatever you want. A, B, C, doesn't matter. Now what I'm going to do is I'm going to test the confidence intervals for each of the different pairwise comparisons. I'm going to do small, medium, small, large, and medium, large. Any of them that are significantly different, I'm going to do nothing to. But if there's not enough evidence, or more to the point we would fail to reject a difference in those two specific means, I'm going to put a line over the corresponding means to indicate that they're the same. And once we get it done, we'll be able to use this for analysis. Now, I'm going to just use the methods that we've talked about before, so mu1 minus mu2, or in this case, the mean of small minus the mean of medium. Typically, with multiple values like this, there's some interaction that's going on, and we would use methods by Touquet, Sheffer, or Bonferroni to do multiple confidence intervals. What I'm going to do here is going to be close enough for now. I will show you those other values at a later time, but I'm just going to give you kind of an idea of how to use this notation. Alright, so I've got these listed in 1, 2, and 3, so I'm going to run 2 sample t intervals because we have less than 30 data points in each case, and I have means, so I'm going to deal with the 2 sample t interval. So I'm going to do it for small and medium first. That's list 1 and list 2. So stat tests 2 samp t interval. And that is 0. Alright, so I want to give it data. For the first 2, I want to give it list 1 and list 2. It will be pooled, 95% will be fine, and hit enter. So about negative 1.5 and positive 6.7. So that is our confidence interval for the difference in the two means. Now, I have 0 within the confidence interval. This one is lower than this. This one's less than 0. This one's above 0. So 0 is within the confidence interval. So according to our confidence interval, these are statistically the same, or we don't have enough evidence to indicate that they're not the same. So over small and medium, I'm going to draw a line. Now that line indicates that these two things are statistically similar, so we can't really tell a difference between the two. I understand that they had a different mean, but those means were close enough to be considered the same. We're going to do the same thing, this time list 1 and list 3. That's the only thing I'm going to change, list 1 and list 3, so it's small minus large. And this confidence interval goes from 1.5 to 9.9. Alright, now these are statistically different from each other, and we can tell which one's the largest one anyway. Our small ones are going to be the larger ones, but since we're taking that minus the other and it is positive, we've got information as well that the difference in the means is going to be between 1.5 and 9.9. So we leave these two alone. Small and large are statistically different. They don't get a line above them. And our last one, we're going to do medium and large, so list 2 and list 3. Test 0 for the ones I need, whatever it is you need to scroll down. So this one will change to list 2. And we calculate, and this goes between negative 1.1 and positive 7.3. So again, these are indicating a difference between the two. So I'm going to draw another line over medium and large, indicating that these two are statistically the same. Alright. Now we can use this for analysis. So we know that small and medium are the same. We know that medium and large are the same. We know that the small is different from the large. Alright, so significantly speaking, if we need this to be lower is better, we would probably go with either large or medium. And if it's high better, then small or medium is what we're going to go with. But we know that small is statistically different from large based upon this.